So for lesson 4, we get into this idea of working with functions as well as function notation. We've been seeing them for a while, so they shouldn't be overbearing for us. But we're going to start with the most basic definition that we have in mathematics. It is a pairing of input versus output functions. You know, if we are pairing Cole is going to go to Gavin or Haley is going to go to Abby, that'd be a relationship, okay, or relation. The pairing of objects or the pairing of numbers. You know, if we say 1 is going to go to 3, 2 is going to go to 4, and so on. Okay? Anything that we deal with in math can always be considered a relation. Here's an example of that. The domain are your input values. What we send them to or what the result is going to be the output or the range. So that would be an example right there. Notice it doesn't always have to be just with numbers. Obviously in math we deal with a lot of our values. But it can be anything. It could be numbers, letters, it could be objects, so on. So we begin with the idea of having a relation, but now we want to get a little bit more specific with that relation. Okay, it's kind of like with our real numbers. We started with the real numbers and then we started identifying them as rational or irrational. And then the rationals we went even further. Integers, whole numbers, and counting numbers. Okay, so a mapping between two sets that associates with each element of the first, the domain, with a unique element of the second, the range. This is called a function. I would not copy the definition down. I would not worry about this. I apologize if you started already. But maybe something that would be more helpful to you are these examples. We have to be very careful about the definition, or with how we go about defining a function. Again, it is a mapping between two sets, x to y, or domain and range, that associates with each element of the first set with a unique, which means one and only element of the second set. So this uniqueness idea can be kind of tricky because the wording when we define this thing it's tough to be able to explain it that way. Both of those that you see are examples of functions. XY table is going to be very common in Algebra 2. Your bubbles, domain and range, are also very common. But the idea is, notice each one of these x's only go to one y. There is your uniqueness part of it. That's really the key part of it. Good to move on? I'll save the video for later on. Let's go ahead and get into my example. Again, functions can be very difficult to describe and explain. And most basic definition is that we have is it's a rule of assignment. We are assigning some x to go to a particular y. And the best example that I can come up with is the classroom/student assignment. Okay, so you guys in this room right now, all, let's see, 9 of us, you guys are the x's. You are the domain. Okay? And the game is I am going to assign you guys to a particular room in the building. Okay? So here are your scenarios. Scenario 1. Let's say I want to assign Hunter to go to room 408. Is that possible? Most certainly. Okay? Assuming you know where the room is at, Hunter himself can go to that one particular room, 408. Okay? Nothing wrong with that. Suppose I want to assign Haley, Abby, and Addison to go to room 409. Now I am sending 3 X's to the same Y room. Is that okay? Is that possible? Don't know if it's okay, but it is definitely possible. It is okay. All right? We can send as many students to one room as we want. Okay? I could send all of you to the gym if I wanted to. Okay? That would be fine. The problem is when I want to send Paige to room 210 and 211. We are sending one X to 2 different Y locations. Is that possible? No. Okay? Paige is just one person. We have not figured out cloning, or at least not at the Pierce High level yet. Okay, we are not bacteria. We cannot split ourselves apart. Okay, so as soon as we start to send one X to 2 Y locations, that's when we have an issue with it. That is when it's no longer going to be a function for us. All right? Hopefully that's helpful. If you go back to the definition, you read it another time or two, that's where you'll start to understand this uniqueness part of it. Examples, if we look at example 1A, we have students 3 and 4, and we are sending them to room 3. Is that okay? Yeah, most certainly. We can send as many students as we want to that one. So which of the following is a function? This one is a function. And then it wants you to identify the domain and range. D and R are more than enough for me. So domain is 3 and 4. You don't have to write them in sequential order. If you want to, that's fine. Range is 3. If we go to part B, function or not a function? Abby, you're saying no. Do you have a reason why? It is a relation. Very good. Yep. Anything that we deal with is a relation. But why is it not a function? You're right. Not a function. Can we explain the why part of it? Or Hunter?
Well, because you have 5 going 2 different Ys.
If we take a look at this student 5, we first told him to go to room 3. But we also told him to go to room 4. And that's where the issue lies. We can't send one student to 2 different locations. Okay? Can't be at 2 places at once. This is the issue. Therefore, it is no longer a function. Again, if we wanted to, we could say it's a relation because we are pairing objects together. But we can't go as far as saying it's a function. We identify the domain. It's 5 and 7. Again, if the numbers repeat, you don't have to list them again. One time is fine. Range is 3 and 4. 2 good examples that you'd like to keep in your notes. So the student/classroom assignment is, in my opinion, is the best one that I could come up with for you guys to kind of keep the bubbles and the charts examples for you. The other way that we can depict relations is with graphs. And when it comes to looking at a graph, how do we determine whether or not a relation is going to be a function? Does anybody remember what that test is called? Good. The vertical line test. And if you have not heard of the vertical line test, basically what it does is it's a test to determine whether or not that graph is a function. And here are the rules. If you can draw any given line, vertical line that is, on the graph, it can intersect at most how many places? The answer is once. If we look at the first one, they drew in 2 vertical lines there. 1 point of intersection, 1 point of intersection, and if we drew in any other vertical line, we would find at most one place. Therefore, that graph is a function. If we look at the second graph, a circle, they drew in this line right here. And if you go back and you look at your points of intersection, notice we have 2 places. And as soon as you have more than one place, not a function. All you need is one vertical line that has more than one place of intersection, and then it's broken. Not a function. We can still say it's a relation because it's the pairing of values, but it's not a function. Vertical line test examples, if we look at 2a, Abby, function or not a function? Not a function. If I put that vertical line simply right on the y-axis, or if I go a little bit to left, notice I have several points of intersection. More than one, therefore not a function. If we go to graph 2, our initial thoughts may be, well, no way, that's not a function. I mean, look at it, it's an arc. It's not even completed. It doesn't even go over here to the left. But does it satisfy the vertical line test? Yes, it does. Okay, even if we draw in this vertical line over here. Again, the definition of a vertical line test is at most one location. Okay, here we have 0 points of intersection. But again, it's okay. Same thing there, at most one. So function. If we go to graph C, function or not a function? Function. Most definitely. Okay, function notation. Students struggle with this idea, and I guess it's just something new, but it's really, really simple. Function notation is no more than taking our typical y equals 4x minus 5, and instead of writing the y, we are now replacing it with this notation f of x. Same idea with the second equation, y is equal to negative 3x. If we wanted to, we could call something different other than f of x. We could call it g of x. And there's a couple of different reasons why we like to use function notation. Number one, we can use different letters or different names to distinguish the difference between certain functions. If I tell you to use the function f of x, you know specifically to use this one. If I told you g of x, you know specifically to use that one. Okay? If I just told you to use one of the equations, well, you wouldn't know which one. I would have to specifically say 4x minus 5, use that one. So we use function notations to name the function itself. That's, in my opinion, reason number one. Reason number two is it allows us to demonstrate and represent the x and y values that we used and what we came up with. And we'll see that here in example number 3. They tell us h of x is equal to 4x minus 3, p of x is equal to x squared minus 3 of x, and they want us to find p of negative 3. What in the world does that mean, p of negative 3? What does this mean right here? Well, it simply means, or Abby? Simply means that we want to take the value negative 3 and we want to plug it into the p function. Okay. First of all, we were able to identify which one of these two we wanted. We want the p function. And now it also tells us in our function notation we're using the x value of negative 3. So you take wherever you see the x's, you plug in that value, and now you evaluate. We did this the other day. And it is from this statement right here. If you ignored all this and the only thing that your partner gave you was p of negative 3 equals 18, there's a couple of different things that you could come away with it. Number one, you would establish that, hey, we used the p function. Okay? Second thing you could say is, okay, when they used the p function, they plugged in negative 3. That was the x value that we evaluated for. The result, what we came up with, was 18. So it is a nice simple notation to identify not only the function we used, the value that we used, but also the result that we came up with. And it's with that idea that makes the function notation very, very nice to use. I'm actually not going to have you do group work for this one. I'm going to walk through this one together. But this is some of the examples that they'll give you in the book, also very good test questions as well. Company charges 25 cents per minute for a cell phone call. This can be expressed as the ordered pair 1, 0.25. They say to find the cost of a 2-minute, 3-minute, and 4-minute call. Express the answers as an ordered pair and set notation. Identify the domain and range, and determine whether or not this thing is a function. Awesome, right? Lots of things going on here. We'll start with this first idea, finding the 2, 3, and 4-minute calls. And they tell us they want us to do this in set notation. So, set notation, the first one they gave us was for 1 minute, that's going to be 25 cents. If we are on the phone for 2 minutes, how much is that going to cost us?
50 cents.
Mm-hmm. So we're going to express it that way. For 2 minutes, that's going to be 50 cents. How about if we are on the phone for 3 minutes? 75. And if we're on the phone for 4 minutes? So it is very wordy in what they want, but the answer is actually a little bit simpler than what they make it out to be. There's the list of your ordered pairs, X, Y's, the minutes, and the amounts that go along with them. Identify the domain and range. What's the domain that we're looking at here? What's that? Yeah. Range? Yep. So you can just go ahead and list those. Lastly, determine whether or not this set represents a function. Yes or no? Yeah, it does. Okay, for every x that we use, we're going to come up with a different amount. You know, you don't have to worry about if you use the phone for 6 minutes, you're not going to get 2 different amounts. You're always going to get one.